Hello everyone, welcome to the Audio SoC SDK introduction of Realtek. Today, I would like to introduce you to the RTL87X3E's hardware. Today's presentation covers the following topics: hardware design, application circuit, layout guidelines, reference design and key parts, QVL. This report is mainly some introductory content. For technical details, you can go through the documentation inside the SDK in detail. Now let's go over the hardware design. The RTL87X3E is a single-chip Bluetooth SoC audio solution for smartwatch and TWS stereo headset applications. The RTL87X3E is qualified for Bluetooth 5.2 specifications, and the embedded hardware modules include a low-power MCU, a low-power DSP, high-performance audio codec, power management unit, ADC, ultra-low current RF transceiver, and smart I/O distribution controller. The BB2 series has different sizes and types of packages, including the smallest 40-pin and the largest 149-pin, and the package types include QFN and BGA. This is the package schematic diagram of RTL8753E QFN40 and RTL8773E in QFN46. The pin distribution of QFN is the same as in the picture. This is the package schematic of the RTL8763EFL in QFN40 and RTL8763EWE in QFN68 package. This is the schematic diagram of the RTL8763EWM. The size is 6mm plus 8mm in a QFN76 package. The pin distribution of the QFN is the same as the picture. The following figure is the package schematic diagram of RTL8763EW in BGA149. The size is 4.9mm plus 6mm. Its ball diameter is 0.22 mm, and the ball pitch is 0.35 mm. This figure shows the power architecture of BB2. VBAT is the main power input. When the VBAT voltage is input, it will be converted into 1.2V and 1.8V through the two internal switching power supplies, which will supply power to the CPU and codec of the IC respectively. The RF part will have an LDO that turns out 3.3V and connects to the pin of the RF input pin. The AVCC_DRV 1.8V in the codec part will pass through the internal LDO and transfer out the mic bias to supply power to the mic. At the same time, the IC can also use ADPIN as the power input, generally as the input of USB 5V, which can charge the external battery on the VBAT. When 5V is connected to ADPIN, IC will work from the power supply of 5V and charge VBAT at the same time. VABT is the power supply for the entire IC. Its operating voltage range is generally 2.8V to 4.5V. If it is lower than 2.8V, it will cause a reset or failure to boot. It also supports the application of external lithium batteries. For the 87X3E series, in order to cost down, the maximum voltage on VBTA is 4.5V. When powered by a lithium battery, the SoC supports power learning management to read the power on the mobile phone. This function needs to fill in the voltage value corresponding to different power in the MCU tool. Generally, it is recommended that customers make a discharge curve for the selected battery. First discharge the battery with 5 to 10 mA, and then put it from 4.2V to 3V after full, and then divide the range into 10 even sections and write down the different voltage values. Fill in the power meter in the MC tool, so that the mobile phone can read the power value when the headset is connected. BB2 series supports software under voltage protection. When VBAT voltage is lower than the voltage set by SWUVP, the system will enter power down mode. The RTL87X3E supports an integrated charger for Li-ion battery application. The Li-ion battery charger in the RTL87X3E series is very flexible for customers using various Li-ion batteries. It supports both 4.2V and 4.35V Li-ion battery packs. The charge to full voltage can be programmed in the UI tool by the customer, with a maximum of 300 mA with thermal protection. Support at command to show the battery gauge, percentage, on the smartphone. The figure below is a battery voltage versus charger current curve across different charger modes. It can be divided into 4 stages: trickle charger mode, constant current, constant voltage, and recharge mode. Number 1, trickle charger mode. If the battery voltage is below 3 V, the charger will charge the battery with a low current of 0.1 C. If the battery voltage does not rise up to 3.0 V before timeout, the charger will be in error and stop. Number 2, constant current mode. If the battery voltage is over 3.0 V, the charger will be in constant current mode until battery voltage reaches 4.2 V. The constant current is defined in the UI tool by customer product definition. Number 3, constant voltage mode. If the battery voltage reaches 4.2 V or 4.35 V, the charger will go into constant voltage mode and the charge current will start to drop until reaching 0.1 C. Note that the stop current can be defined in the UI tool by customer. Number 4, recharge mode. If the battery charge process is completed, the charger will stop charging the battery. If the adapter is not removed and the battery voltage drops over a period of time, the charger will restart the charging process with CC and CV mode configuration. The charging module supports ambient temperature detection. When the ambient temperature reaches the set error range, the charging will stop. When it reaches the warning range, the charging current will be halved. The values of the error and warning can be set with the MCU config tool. The entire temperature detection is achieved by sampling the voltage value of the ADC divided by the external thermistor voltage. When it is not charging, LDOAUX may not be turned off, which will then introduce additional power consumption. Therefore, it is recommended to connect to MOS with the thermal resistor and use the USB to control the switch of LDO_AUX. In addition, in order for the ADC to have a higher accuracy, a 0.1 UF capacitor must be attached to the ADC pin in the mode of limiting the voltage of 1 V. According to the different voltage values of LDOAUX, we provide the corresponding selection value and thermal resistance type for selection. For more information, please refer to the documentation in HDK. Cut 16. The output of the switching circuit is a PWM wave. It is necessary to add an additional LC filter circuit at the output. The value of the inductance of the filter circuit is 2.2 microhenries, and capacitor is 4.7 microfarads. This value cannot be replaced and must be used according to our reference design. The selection requirements for inductors and capacitors are relatively strict, which will be described in detail in the QVL section later. It is recommended to choose from the recommended models in the QVL list. The following picture is the part of hardware reset. The HW-RS-N pin is active low. There will be an internal 10K ohm pull-up resistor and an external 1 UF capacitor that is required to prevent interference from other signals. If the hardware reset pin continues to be pulled down for more than 5 to 8 milliseconds, the hardware will reset the entire system. The IC also needs an external 40M crystal as the clock source for the CPU and BT signals in normal mode. The specifications of crystal selection should also meet the requirements of the QVL. There is a set of adjustable capacitors inside the IC to calibrate the frequency offset of the crystal oscillator. According to the QVL, choose a crystal whose CL is 7 PF or 9 PF, and you can use the internal adjustable capacitor to calibrate the frequency offset of the crystal. If the selection of the crystal oscillator does not meet the QVL selection, it may exceed the adjustable range of the internal capacitance, and additional external capacitors need to be added, otherwise there will be a large frequency offset, resulting in risks such as Bluetooth disconnection. Differential output. Please note that the AOUTP and AOUT need to be reversed, that is, AOUTP outputs a negative signal, and AOUT outputs a positive signal. Our analog output has good quality. The SNR can reach 106 and 104 database administrator, and the noise floor can reach 106 database administrator. The following figure is a schematic diagram of the connection method of the differential output. The output of the negative terminal is a signal opposite to the positive terminal, which can cancel the DC bias of the positive terminal signal, so that there is no need to add additional DC blocking capacitors to improve the anti-interference ability. The Class D output can be directly connected to a 16 ohm or 32 ohm speaker without adding PA. If the connection to the SPK is too long, a series magnetic column and a parallel capacitor need to be added to avoid EMI interference. The audio input supports the input methods of AUX-in and digital mic, and supports 4 channels of AMIC input. A mic supports 2 analog to digital inputs, and the input SNR can reach up to 96 dBA. Its resolution is 24-bit, and the maximum sampling rate is 96 kHz. The maximum sampling rate of D mic is 192 kHz, and it supports 4 channels of PDM mic input. The RTL87X3E has a fully integrated radio transceiver compliant with the Bluetooth SIG test specification. Designed for low power consumption and excellent transmit and receive performance in the ISM band. The RTL87X3E supports Bluetooth Classic and Bluetooth BLE for all packages. TX radiation power is up to plus 10 dBm. Transmitter. The transmit mixer module modulates the baseband input signal to the ISM band and is designed to provide good stability and modulation characteristics. The power amplifier, PA, integrated in the chip can provide up to 10 dBm in the ISM band. Receiver. At the receiver signal path, the low noise amplifier, LNA, is to amplify low power RF signal to the desired signal level without significantly increasing the noise power. Subsequent to LNA, the receive mixer demodulates the received RF signal to the intermediate frequency band, and then the IF signal is passed to the modem to decode the received signal. The synthesizer is a control loop to compare the crystal and VCO during their phases. If the VCO frequency shifts, then the phase difference produces an error signal for the control loop. The RF circuit needs to add a pi matching circuit. The impedance matching network on the chip side is used for harmonic suppression. For the selection of pi matching components, refer to reference design. As shown in the figure below, choose to use the exact same part as in the QVL, otherwise the RF performance may not be guaranteed. The impedance matching device value at the antenna end is determined by the antenna part, and in some designs, the impedance matching network of the antenna can be implemented using only 2 components. However, it is recommended to reserve 3 device package pads in the PCB design for minor adjustments in the final stages. The choice of antenna in hardware design includes PCB antenna, ceramic antenna, thimble antenna, etc. There are 3 points to note. Number 1, if a PCB antenna is selected, a complete clearance area needs to be reserved, otherwise, the radiation characteristics and center frequency may be affected. Number 2, in the direction of the antenna radiation, there can be no metal components, such as batteries, speakers, etc., which will block the radiation of radio frequency signals. Number 3, RF signal traces must be designed with a characteristic impedance of 50 ohms. Ceramic antennas are recommended if space is limited in the antenna exclusion zone. Ceramic antennas are small in size and have superior stability. It is recommended to use an antenna with a larger package. There are optional antenna manufacturers listed in the HDK, and they can provide a complete solution. The thimble antenna is also a common antenna scheme, which has certain requirements for the housing. The distance between the housing and the PCB must be greater than 10 mm to ensure good radiation characteristics of the antenna. When using the thimble antenna, the RF path needs to add a DC block capacitor to prevent the chip RF from being damaged when the thimble is soldered. When debugging the antenna, it is recommended to assemble the whole thing and debug it according to the complete usage scenario. Debugging with a bare board may not have the influence of the case, battery, and speaker, and the measured characteristics are inaccurate. And it must be carried on the dummy head for debugging. Because the human body will also affect the performance of the antenna, it is also recommended that you test its field type and efficiency in the laboratory to check whether the design of the antenna meets the requirements. The suggested radiation pattern of the antenna is that the antenna placement of the left and right ears should be symmetrical. The direction of the maximum gain of the antenna radiation should be far away from the human head. In the direction of the human head, it is better to radiate a little weaker, because the human body will have a certain absorption effect on electromagnetic waves. SoC has a wealth of peripherals. There are multiple groups of GPIO to choose from. There are timers that support PWM function, I2C, SPI, and UART with a maximum baud rate of 4M. It also supports 5V 1-wire UART on a DPI-N pin, 16-way GDMA, for channel ADC and 12-bit resolution. Besides, it also support keyscan, support will encoder, decoder, infrared, SDIO, etc. Next, introduce the application circuits. The 1.2V after the switching regulator is filtered by LC will supply power to the CPU and RF circuit. A bead must be connected between VDD1V2 RF and VDD1V2. The model of this bead cannot be replaced and needs to be selected from QVL. The main requirement is that the magnetic bead has an impedance at 1 MHz, which is used to filter out the interference of the digital circuit to the RF circuit. Note that the two 4.7 microfarad capacitors on HV and LX core have particularly high requirements for ESR, and it is best to choose according to our QVL. The RTL8763EX series mainly has two LDO-AUX. One is LDO-HV33, which is fixed at 3.3V and will supply power to the flash and cannot be configured. The other is LDO-AUX, which can be configured with voltage in the MCU tool and can be adjusted from 1.8 to 3.3V. In-ear detection is supported on the hardware. HX3001 has a reference circuit in the reference design. The power supply requirement is 3V, connect GPIO through LD- and control whether the internal laser works through GPIO. The VOUT pin is used as the signal for in-ear detection. The IC supports the photoelectric detection of the I2C interface, such as JSA1225, which can be configured in the MCU tool. Also supports special calibration processes. In addition, we also support 3-axis accelerometer for functions such as tap detection. It is necessary to configure the I2C and INT functions in the MCU tool to perform actions such as tapping to wake up the IC, which must be set in the tool. It is suggested that the I2C function should not be assigned to the ADC 0-4 pins. These are analog pins, which are in short supply, and should be assigned to the digital function pins first. Do not assign it to the I/O of the FDIV domain, because mic P, mic N, and other pins also support digital functions, but after entering DLPS, these pins will normally sleep. If they are connected to these pins, then it will increase the power consumption budget. The figure below shows the reference circuit of the RTL8763EM/EM-S mic through differential connection. It is recommended to use the differential connection method to connect the MEM-S mic and the RTL8763E chip to reduce the interference of common mode noise on the PCB. The reference circuit of the omnidirectional condenser mic connected to the RTL8763 in differential mode is as follows. Also note that the EMC Plus is connected to mic N through a capacitor, and the ECM is connected to mic P through a capacitor. The 10 PF capacitors on mic P, mic N cannot be reversed. The IC supports most D mics in PDM format on the market. Any I/O pin on the RTL87X3E can be connected to the CL-CAN data pins of the digital microphone, but it should be noted that the maximum voltage of mic BIAS is 1.8V, and all data and CLK must select 1.8V I/O. IC supports D mic sampling on the rising edge as well as sampling on the falling edge. So we can control whether it is active high or active low through the pin of mic select. Just like this picture, realize the clock and data of 1D mic to read the signal input of 2D mics. It also supports the function of AUX in. connect the L and R of AUX in directly to AUXL and AUXR. Generally, a GPIO is reserved for AUX in insertion detection. Please note that when the codec is Class D plus speaker output, in order to ensure the quality of the output signal, it is recommended to reserve the position of the bead and capacitor to eliminate EMI interference. External amplifier. Since the Class D output is a square wave, the RLC circuit as shown in the figure below needs to be added for filtering before the signal enters the amplifier. Special attention that keeping the packages of L and C unmodified. The values of L and C are different for different PA product types. The general recommended selection value is the combination of 6.8 A plus 100 NF. For details, refer to QVL. The RTL87X3E supports 3 analog microphones, Mic 1, Mic 2, and Mic 3. Mic 1 is treated as main microphone always, and Mic 2 as the second auxiliary in dual microphone applications. If BB2 selects the input of ANC, it can be set through the ANC design tool. It is also recommended that when selecting the mic of ANC, do not select the capacitive ECM mic. Because the power supply rejection is relatively low, it will affect the effect of ANC. The RTL87X3 supports high-quality ADC input, designed in 12-bit, and can be multiplexed with the digital GPIO function. For all ADC channels, maximum input voltage must not exceed LDO AUX level. AUX ADC full scale swing is 3.3 V. RTL87X3 supports 2 input mode and 2 sampling mode. AUX ADC input impedance was very high in the bypass mode. ADC full range would be 0 to 0.9 V in this mode. The bypass mode is suitable for the application which needs high input impedance. In the divide mode, the full operating input range of ADC is 0 to 3.3 V in this mode and is suitable for the application which needs to directly connect to external power source input. If it is used to detect the ambient temperature of the battery, we recommend dividing the sampled voltage value to within 1 V. In addition, a 0.1 UF capacitor is added to the ADC pin for filtering to ensure that the ambient temperature detection accuracy reaches plus and minus 1 degrees. The following is a brief introduction to the layout guide. First of all, I will introduce some priorities for overall layout considerations, which should be strictly followed during layout. First, the first consideration is whether the relationship between the placement of key components and the shell is reasonable or feasible under the premise of ensuring product functions. For example, whether the antenna should be placed on the casing, the way of in-ear detection and the signal receiving point, the location of the mic, and so on. Second, after meeting these requirements, the most important thing is the cap and inductor of SoC power. Then follow the order of power component, RF, antenna and RF trace, crystal, audio, USB, GPIO, EMI ESD and MISC. Next, we will focus on the order of placement. Layout should be strictly followed. HV audio and HV core are the inputs of the core buck circuit. The layout of the capacitors on the HV should be prioritized and placed as close to the IC as possible. The trace from the capacitor to the IC should be as short as possible, and the length should not exceed 100 mm. The second priority to consider is that the inductance and capacitance of the buck circuit should be placed close to the IC. The DC-DCLX pin, through inductors and capacitors, forms a stable, low-noise voltage source, first through the inductors and then capacitors. Branching out without capacitors is strictly prohibited. Considering the EMI problem, the LX signal line must be short and thick, and the trace width is recommended to be more than 15 mm. The third thing to consider is the capacitance on the ADPIN and VBAT pins, as close as possible to the IC pin. The ground terminal of the capacitor should be as close as possible to the E-pad of the IC. If there is enough space, the GND via of the capacitor can be placed 3 times, so that the return flow of the GNG is better. Then there are components such as RF devices and crystals, which need to be as close as possible to the IC, and ensure that the lower layer has a complete signal. There are many other considerations. The audio trace should be kept away from the interference of the power inductance. Bypass CAP. The bypass capacitor is placed close to the input end of the power pin, and the return flow is not blocked. It normally returns to the GND of the chip and the independent via is grounded. The via hole is as close to the capacitor pad as possible to reduce the return path, as marked in the figure below. The power traces must pass through the capacitor before entering the IC or outputting to other branch power supplies. The RF trace needs to do 50 ohm impedance matching. Components must be placed in a straight line and as close as possible without introducing additional traces. In addition, there must be a complete reference GND below the RF trace to ensure that the return path is unobstructed, otherwise it will affect the RF power. The reference plane of RF matching components and traces must not have any signal lines crossing through. The antenna area needs to be empty, there should be no copper, and there should be no signal lines under the antenna. The antenna reserves as much space as possible in order to use a larger antenna to obtain higher radiation efficiency, larger operating bandwidth, and sufficient air exclusion, as shown in the figure below. The forbidden space between the antenna and the ground needs to follow according to the datasheet of the antenna in order to obtain the radiation field pattern and efficiency with excellent performance. GND via should be used on both sides of the RF trace to reduce interference from external components. The antenna reference ground is returned to the chip ground as soon as possible. The antenna return path needs to be the shortest distance, no obstruction, and good connection. The GND via of the RF component should be as close as possible to the PAD. A GND via should be grounded separately, not connected to the top layer copper foil, and the copper should be covered with a connection. In the following two pictures, the copper cladding in the right picture is incompletely divided by the traces, and the left picture is better. The signal lines DM and DP of USB need to be differentially processed, and the impedance is required to meet 90 ohm plus and minus 15%. The layers adjacent to the USB traces must be complete ground planes. The distance between the USB trace and other traces is recommended to follow the 3W principle. The USB transmission line should be on the same layer, and there should be no vias through the layer. In addition, try to avoid branch traces and vias to avoid introducing parasitic effects. For the crystal, it should be placed as close to the IC as possible, the path should be short, and the trace width should be greater than 6 mm. At the same time, it is recommended to ensure that there is a complete ground below to ensure a smooth return path and reduce the impact of EMI. In the absence of structural constraints, crystal and BT chip should be placed on the same level. To avoid interfering with RF signals, crystal keeps RF trace as far away as possible. A capacitor is usually attached to the power pin. The layout should pay attention to the current flow. It must first pass through the capacitor and then enter the IC pin to ensure the filtering effect. The switching power supply layout needs attention to be paid to. First, the filter inductor and capacitor must be close to the IC, and the trace width should be over 20 mm. Second, do not run the signal line under the inductor, because there is a high-frequency switching signal on the inductor, which may affect the data signal below. Third, the path of the capacitor back to ground should be as complete as possible to ensure that the ripple is as small as possible. Fourth, it is recommended to ensure a complete ground below the inductor to obtain a better EMI suppression effect. Then the audio signal, such as speaker and mic-related traces, need to go through differential lines. For example, the SPKP, SPK NAND mic N mic require the differential trace width to be greater than 8 mm and the spacing to be less than 6 mm. However, AUXLIN Lambda UXINR cannot be used as differential lines, and the two signals should be separated by GND as much as possible. Do not overlap parallel traces on adjacent layers of the PCB. There is no copper between IC pin PAD and EP pad, and the GND pad must be directly connected to the second layer, GND layer. The middle of the EP pad should be marked with GND via and connected to the second layer, GND layer. Reference design will be provided in the early stage of product development, just contact the engineer to provide it. The last part is key component and QVL. As shown in the following table, the selection of 40M crystal needs to meet the requirements in the following table, specifically. 1. Need to meet frequency tolerance plus stability are smaller or equal to 20 ppm. 2. Select 7 or 9 PF for CL. 3. The maximum drive level must be 300 microwatt. 4. ESR requirements. 5. The insulation resistance should be greater than 500 m. QVL will provide links to some manufacturers and recommended models for reference. Then the 32 kHz crystal needs to meet the requirements of the following table, CL equals 7, and the frequency error should be plus or minus 20 ppm. Optional manufacturers are also listed in the table. Power inductor for SWR introduction. The selection of filter inductors on switching power supplies is very important. It is recommended to use wire-wound inductors. The ISAT of stacked inductors is generally low, so it is not recommended to use them. The inductance value of the inductor is 2.2 microhenries plus or minus 20%. The self-resonant frequency should be greater than 40 m, and the DCR should be less than 0.6 ohm, preferably between 0.1 and 0.3. The critical current value should be greater than 500 milliamperes. Here are the models for reference. The critical current refers to the maximum current when the inductance value drops by 20%. The datasheet of some inductors will list the rated current, which is its power value, not the critical current. Pay attention to the distinction. Make sure that ISAT is greater than 500 milliamperes, so that the inductance value of the inductor will not drop under high current, and the ripple of the power supplied will be small. ANSY's mic should pay attention to the power output of mic BIAS is 1.3 to 1.8 V. The typical is 1.6 V, and the spec of the mic should be able to work under this voltage. In addition, the mic model and brand of the left and right ear should be the same. There are more detailed ANC mic spec requirements and recommended models in HDK. I won't go into details here. In the RF part, the inductance and capacitance values of the pi matching circuit here or the model of the low-pass filter cannot be changed. Other values cannot guarantee the effect of filtering out high-order harmonics, and may affect the results of test certification. The inductor manufacturer for low-pass filtering is Murata, and the capacitor manufacturer is Waxink. Best not to replace it. This slide shows some manufacturers of complete antenna solutions that are recommended, which can provide a standard test environment to test the antenna effect of the whole machine, which is convenient for everyone to contact and test. Thank you for watching our RTL87X3E hardware introduction. For more details, please read the HDK documentation carefully. If you have any questions, please feel free to contact us. Thank you all.